So the reason why we need to think about log base 2 is that when you look at a culture over time and the number of cells in any particular culture, you see that there's sort of a predictable way of looking at the culture. There's the lag phase in which the cells are sort of getting ready to change their metabolism, getting used to the new environment. There's the log phase in which they're growing as fast as they can grow and under the conditions in which the culture finds itself. And then there's stationary phase. And in stationary phase, they've run out of room, or they've run out of nutrients, or they've run out of something. And so the cells stop or slow growing. Now, what you notice about this S-curve is that the S-curve here it's kind of difficult to say exactly when the log phase and the lag phase transition is, and so I kind of guessed by putting this line here, but it'd be nice to know exactly when those things happened. And we can do that if we have a different mode of looking at the cell growth, and that is by looking at it as if we were looking at generations. And so if we thought about this as generation time, so number of times it doubles, then what we'd find is that during lag phase, not much would happen. During log phase, we would have a single line. And during stationary phase, we would have a very nice linear slope to our line, or in this case, no slope, so stationary phase. And now the transitions between these points are very easy to see, and the slopes are easy to measure. So how do we go from the sort of S-curve model to this very straight linear model where we can see and differentiate these different phases of growth? The answer is using log base 2 calculations. So the way to explain log base 2 is that if you understand that one cell divides to become 2 cells, and 2 cells divide to become 4 cells, and 4 to 8, and 8 to 16, what you know is that each one of these can be considered a generation. So the first generation is 1 to 2, the second generation, third, fourth, etc. So what we know is that if you think about the log base 2 of any number, it's really the number of generations it took to get to that number. So let me say that in a different way. Let's look at the number 2, for example. If we take the log base 2 of 2, it's equal to 1. And that correlates to the first generation. If we take the log base 2 of 16, that is equal to 4. And that correlates to that. So what that means is that if I take the log base 2 of any numerical value, that I should be able to tell how many times that culture had to double to get to that number. So, for example, if you were to take a number such as 1 million, and you ask the question, how many generations? Does it take to get to 1 million? You could just take the log base 2 of 1 million and figure that out. So I'd like you to stop the video here and go to the calculator, put in 1 million, calculate the log base 2, and come back with a number. Okay, so what did you get? I got that the log base 2 of 1 million is equal to 19.9. So approximately 20 generations. All right, so let's do the hard work and figure this out. Let's prove to ourselves that So 1 to 2 to 4 to 8 to 16 to 32, 64, 128, 256, 512, 124, 1024, 2048, 4096. Oh, that's so tedious. Who wants to do that? None of us. But how many generations do we have just to get to 4096? We're going to check. So 1 generation, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 generations to get to 4096. So my prediction is that the log base 2 of 4096 is equal to 12. Go ahead and do that calculation on your log base 2 calculator. I'll wait. All right, and if you checked, what you find is that indeed it's 12. So do you see that this is really just a way of keeping track of how often these numbers double? Okay, so what does that mean for cell culture and cell doubling? Let's go back to the graph. So now, instead of cell number over time, if we have log base 2 of cell number, and in fact we know that that's essentially equal to generation, what we end up getting is a very distinct lag phase, a very clear log phase, and a very clear stationary phase. And so now when we talk about the cell culture, we have lots of pieces of data to think about what's happening in that culture, how long it takes to come out of lag phase, how fast it is in log phase and exponential growth phase, and how soon it goes into stationary phase. All of these pieces of information are very important in understanding how a cell or a culture of cells is responding to its environment.